Welcome back. This is week 4 of inverse methods in heat transfer. In the last video, we looked at gradient descent and looked at a very simple example on how to do gradient descent, which was somewhat successful if we played with the value of the learning rate alpha. In this video, we would like to try gradient descent for I forgot to write descent here. So we would like to try gradient descent for a nonlinear regression problem, which is our initial aim. So I'm going to introduce the data set here. We have a slightly modified data set from here within your assignments for this week. But let's just consider it and see whether we can figure out these constants A and B. So as usual, let's not as usual, but as we discussed earlier on in this week, let's consider the heating of a first order system. So a first order system, remember, was a system which had some amount of heat transfer Q, which was heat generation Q, which was being added. And there was also some convection H. And finally, we saw that in such a case, the temperature distribution or the temperature excess distribution, in case outside temperature is T infinity, looks to be in the form theta is A times 1 minus e to the power minus bt. Now, the problem with this was that this you could not solve using linear regression because this is not a linearizable form. So this was not linearizable. And this is why we started looking for some methods that would generalize to nonlinear equations also, or nonlinear optimization problems. And one such example was gradient descent. As I said, we will be using it again when we come to the machine learning portions of this course. Now, let's say we have two initial guesses. We have already seen gradient descent and we have two initial guesses, A equal to 35 degrees and B is 0.004 per unit second. You can check what the units are by just trying to make dimensional analysis on this equation here. Okay, so you can easily check dimensional analysis here. Now, here is the data set. What I am going to do, of course, is after some time, I'm going to refer to the first variable as X and the second variable as Y. And of course, we have our model Y hat, and Y hat would look like it is A 1 minus e to the power minus Bx, because it's just easy to code it once and for all. Now, a word of warning for those of you who will be following me along here, even though I will use a code, okay, it makes no sense unless it's a live class for me to actually show you a hand calculation on the board here. I can do it a couple of times, but it quickly gets boring. It's best for you to, however, do it by hand in case you're taking this course for credit, because you will have to use a calculator in the final exam. We will try to make the problems a little bit handleable by hand, but nonetheless, we won't have access to programming languages when we look at the final exam. So nonetheless, I will motivate the problem, then I'll show you a code for gradient descent, which for those of you who are taking it for credit, it should be available to you through the NPTEL or SWAYAM platform, whichever way you are taking this course. Okay, so in general, we have this data. I'm still going to call it xi, yi, and yi hat. And you can translate it in your mind to actually time the temperature excess, and you can also think of this as theta I hat. The reason I am using this is I would like to employ it in a code. And when I write it in a code, it is generally a good idea for the entire course for us to use the same notation so that we remember that this is the input, this is the output, and this is the model. Okay. So let's start. Some data is given here. I'll, of course, put it explicitly within the program when we come to the program. So we have this data, and our problem is this. As usual, we have to specify some j. Now, j is going to be a function of a and b now. I could call it w also, but I'll retain a and b because a and b is a little bit clearer as far as this example is concerned. So you have the summation. We make a guess for a and b as is given in the problem. So we said a is 35 degrees. This is the initial guess. And B is 0.004, if I remember right. 0.004 per unit second. How did we get these values? Of course, we have some physical idea for what these mean. And if you look at the original forward model for the problem, these come from some physical constraints. Okay, so these are physical guesses. And this is once again where your knowledge of heat transfer will play into getting the right initial conditions for your model parameters. Okay, so as usual, we have the same model. You can call it yi minus y hat I square or y hat I minus yi square, which is the same thing. And what we want to do is to find, remember, del j del A and del j del B in order to use for gradient descent. Even if you want to optimize it analytically, you still need del j del A and del j del B. Now, the way this will be done is, so let's say I want to find out del j del A. That is going to be del j del y hat and del y hat del A, just like we did for linear regression. So this will basically give us del j del A is 1 over m sigma y hat I minus yi. You can multiply, you can look up your notes for linear regression also, multiplied by del hat I yi by del A. Okay. Now, what is this quantity? Remember, y hat is a 1 e to the power minus bx. Again, I am warning you, I am using x, whereas I actually mean t, but I am going to use x just for convenience of notation. So del y hat del A is simply 1 minus e to the power minus bx I, in case this is y hat I. Okay, so we can substitute that here, and it's easy to program. Again, this is easier when you actually have to program. It's a little bit tougher when you have to evaluate it. So as you can imagine, if you have to evaluate it by hand, you will have to do a summation over these 6 quantities. You can write it in columns. You can write del y hat del A in one column, this in another column, etc., etc. Okay, so maybe during the summary for this course at the end of the last week, I'll write that down so that people taking it for credit can employ it a little bit more easily. Similarly, when you have del j del b, that is del j del y hat, which remains the same, del y hat del b, and once again, you can calculate this expression as 1 over m sigma I equal to 1 to m y hat I minus yi multiplied by del y hat del b. And now, given that y hat equal to a 1 minus e to the power minus bxi, del y hat del b equal to a times. Now, this a is a constant because we are taking a partial derivative with respect to b. So this is just a derivative of this term, which is e to the power minus bxi multiplied by, you have to be careful, you're differentiating with respect to b. So the derivative actually becomes minus xi, and the minus and minus cancel, and you simply have xi here. So please be careful about this term here. It's often, I see people get confused here. They will put a b here instead of putting an xi. We are differentiating with respect to b. So it's just a slightly tricky thing that you have to negotiate because of what you're used to usually. Okay, so once again, you can program it this way, y hat I minus yi multiplied by del y hat del b. So this is what is going to go into our program. We are simply going to say that any update for A, the gradient descent update is simply going to be whatever current value it has minus some learning rate multiplied by del j del A. Similarly, B is going to be whatever current value of B it is, alpha multiplied by del j del B. Notice that del j del A and del j del B are a little bit more complicated than what we had in our previous examples. That's because they are summations over the data set. Okay, so this entire data set has to be summed up, and that's how you get del j del A and del j del B. So I'll just show you how to implement this in a program, and then we'll see whether it works or not. So let's go ahead and try it now.